All right, now that we have a pretty firm foundation of stoichiometry and how to solve different types of problems, we're going to kind of combine all that in and solve some bigger AP style problems in this next problem solving section. Example 1. A student is given 50.0 milliliters of a solution of Na2CO3 of unknown concentration. To determine the concentration of the solution, the student mixes the solution with excess 1.0 molar calcium nitrate, causing a precipitate to form. The balanced equation for the reaction is Na2CO3 plus CaNO3, both aqueous, combine to produce 2 NaNO3 aqueous plus CaCO3, which forms the solid precipitate. So part A, write the net ionic equation for the reaction that occurs when the solutions of sodium carbonate and calcium nitrate are mixed. And B, the diagram on the right is incomplete. Draw the species needed to accurately represent the major ionic species remaining in the solution after the reaction has been completed. Here's example 1 continued. That student filters and dries the precipitate of calcium carbonate, which has a molar mass of 100.1 grams per mole, and records the following data. The volume of the sodium carbonate solution was 50 milliliters. The volume of 1 molar calcium nitrate added was 100 milliliters. The mass of the precipitate collected was 0.93 grams. Given that data, in part C, we're going to determine the number of moles of Na2CO3 in the original 50 milliliters of the solution. In part D, the student realizes that the precipitate was not completely dried and claims that as a result, the calculated Na2CO3 molarity is too low. Do you agree with the student's claim? And make sure you justify your answer. And then in part E, after the precipitate forms and is filtered, the liquid that passed through the filter is tested to see if it can conduct electricity. What would be observed? And again, justify your answer. Okay, in part A, we're asked to write the net ionic equation for the reaction that occurs when the solutions of sodium carbonate and calcium nitrate are mixed. So we can see from this list of givens on the left-hand side of our reaction, we have 2 aqueous solutions, but one of our products is a solid precipitate. And so we want to write the overall ionic equation for the formation of that solid precipitate. Okay, so ions that are not involved in the reaction or not involved in the formation of the precipitate, remember that's our evidence that a reaction occurred, are called spectator ions. All they do is hang out in the solution. They don't participate in the reaction, and so we can eliminate them from the overall chemical equation. So take a look at what is it that forms our solid. What forms our solid are calcium and carbonate. So we don't need our net ionic equation to include the other 2 ions, and those other 2 ions would be the sodium and the nitrate. So we can have a reaction that only includes calcium and carbonate. And remember, these are ions, so we want to include their ionic charge. In this case, the sodium and nitrate ions are not part of the precipitate, so they are not included in the net ionic equation. So we have our calcium ion, which is 2+, our carbonate ion, which is 2-, producing our precipitate CaCO3 solid, and that's our net ionic equation. In part B, we're told that the diagram is incomplete and we need to draw the species needed to accurately represent the major ionic species remaining in the solution after the reaction has been completed. We know that we start with 50 milliliters of Na2CO3 and we have a 1 molar solution of CaNO3, okay? And that we form this solid precipitate. So I'm going to go back actually to the question so we can see the diagram as it's given. So we have Na and NO3 ions hanging around in the beaker, And down at the bottom, we have solid calcium carbonate. That's expected as our precipitate forms, right? Now, the thing to note is, so we're missing something here, right? So we know these are our spectator ions. We know that this is the precipitate, but what's missing? So the key word in the question here is that the student mixes the solution with excess 1 molar calcium nitrate, 1 molar CaNO3 okay? So excess means more than we need, okay? So we know that we have more of the calcium nitrate. Some of the calcium is used to form the solid precipitate, right? Some of it is used to form the solid precipitate, but if it's added in excess, then we must also have more, okay? We must also have more. So what we're saying is all of this carbonate reacts. All of this carbonate reacts to form the solid, but we have extra calcium ion, excuse me. So let me go back and show the diagram. So your diagram must include at least one Ca2 plus ion, as it is in excess in the solution. All carbonate ions are precipitated as solid calcium carbonate, as shown. All right, part C of example 1, determine the number of moles of Na2CO3 in the original 50 milliliter solution. So I've listed on the screen the things that were given in the original problem. I know that the volume of my original solution of Na2CO3 is 50 milliliters. I know I added 100 milliliters of 1 molar CaNO3, and I know the mass of the calcium carbonate precipitate was 0.93. We were also given the molar mass of that precipitate, 100.1 grams per mole, and we're given the overall balanced equation. Okay, now we are finding the moles of Na2CO3 that we started with. So before any reaction occurs in the original solution. Okay, so we can do that by figuring out, working backwards from how much product was produced, right? Because we know from back in part B, all of the carbonate was reacted. And so if we take our mass of product, which includes the carbonate, and we work backwards to see then how much did we start with based on how much we produced, we can get our original number of moles. So this is just a straightforward grams to moles calculation. If we had 0.93 grams of calcium carbonate divided by 100.1 grams per mole, that means we produced 0.0093 moles of calcium carbonate. Now we have moles of a product here. We need to use stoichiometric ratio from the balanced chemical equation to find moles of our reactant. So 0.0093 moles of calcium carbonate. Looking at this balanced equation, we have a 1-to-1 mole ratio, 1 mole of sodium carbonate per 1 mole of calcium carbonate, which is 0.0093 moles of sodium carbonate. Again, for every mole of carbonate ion, which we see here, there is 1 mole of sodium carbonate. The student realizes that the precipitate was not completely dried and claims that as a result, the moles of Na2CO3 calculated is too low. Do you agree with the student's claim and justify your answer? So on these types of questions, you can't just say agree or disagree. You won't get credit for the problem. You need to provide a justification for why you agree or disagree. So let's go back really quickly to part C and just see what did we get for the mass of the precipitate. And let's talk about the impact of what would happen to that mass if it wasn't dried completely. So if I go back one question, we had a mass of precipitate collected to be 0.93 grams. Now, if it wasn't totally dried, what's contributing to that mass? Well, what's contributing to that mass is the water that's still there, right? So this would be too high. This would be too high, resulting in too many moles, right? So that increases the estimate, the number of moles of reactant. Okay, so this student says that the calculation might be too low, but if we have too much mass, then that means the number of moles we calculate would be too high. So disagree. The presence of water in the solid increases the total mass of the precipitate. It is now greater than the mass of calcium carbonate. As a result, the calculated number of moles of calcium carbonate and moles of sodium carbonate will be larger because it's including that excess water than the actual moles present. So the calculated moles of sodium carbonate will be too high. Finally, part E of example 1. After the precipitate forms and is filtered, the liquid that's passed through the filter is tested to see if it can conduct electricity. What would be observed? And again, justify your answer. So we can't just say, yes, it conducts electricity, or no, it does not conduct electricity. We have to say why we would observe that. So I'm going to go back to part B. You've already drawn this diagram, okay? So these AP problems, they build one part to the next part to the next part. You can almost always go back to a previous answer to carry that idea forward into the parts later in the question. So look at the beaker. What's in the beaker? We have a mix of ions, right? Sodium ions, calcium ions, nitrate ions, a whole bunch of positives and negatives, right, in the solution. So the question is, would we expect that to conduct electricity? Do dissolved ionic salts conduct electricity? And the answer is yes. The liquid conducts electricity because there are sodium, calcium, and nitrate ions present in the solution. The liquid is now an electrolyte that conducts electricity.